Welcome to the Boring Strong Backend Blueprint, an architecture designed for long-lived systems using Erlang, Lua, ZeroMQ, and Postgres. Key benefits include concurrency mastery, fault tolerance, minimal infrastructure, safe extensibility, and observability. The architecture is built on 4 core components. Postgres serves as the single source of truth for all data and job queues. Erlang/OTP provides concurrency and fault tolerance via supervision trees. ZeroMQ is the brokerless nervous system for fast internal messaging. Lua acts as a sandboxed policy layer for safe tenant logic and rapid iteration. The 4 pillars of the Boring Strong backend are Erlang, offering millions of concurrent processes and hot code upgrades, and Postgres, providing ACID compliance, JSONB, and durable job queues. ZeroMQ enables microsecond latency internal RPC and pub/sub messaging. Lua offers per-tenant rules and logic, safe experimentation, and rapid iteration without core risk. The service responsibilities are divided into 5 roles. The deployment strategy starts co-located for fast iteration, then splits for independent scaling and fault isolation. The core service handles domain logic, and the Lua runner manages sandboxed script execution. The transaction Outbox pattern ensures disciplined data consistency. Commands are processed synchronously by the core service, updating the database and inserting an event into the outbox atomically. Asynchronous publishing then sends the event via a worker service, ensuring strong write and eventual read consistency. The outbox and inbox pattern focuses on durability in the database and speed with ZeroMQ. The core principle is that durability lives in the database. This achieves Kafka-like guarantees for reliable event sourcing without a Kafka broker. We use a Postgres job queue, utilizing the SKIP LOCKED clause for reliability and simplicity. The worker process polls for jobs, locks and processes them, and handles marking them as done or sending them to a dead-letter queue. This simplifies the stack by replacing systems like Redis for reliable queuing. The real-time architecture uses beam-powered concurrency, with 1 Erlang process per connection handling millions. State and subscriptions are managed in ETS for microsecond lookups. Message delivery uses ZeroMQ events pushed to clients with a back-pressure mechanism via bounded mailboxes to drop non-critical events. Script storage is versioned in Postgres with instant rollback via an active pointer. Sandbox execution runs in supervised external processes, limited by instruction gas and hard timeout. This is perfect for ranking, pricing, experiments, and tenant rules. This slide details the architecture for a discovery feed scaling to 100 million daily active users. The data flow involves PostGIS for geoqueries, a Lua ranking engine for scoring, and an ETS cache for feed results. Reliability is managed by the Outbox pattern and ZeroMQ PUB/SUB. The DoorDash fulfillment system handles 50 million orders per month with less than 5 seconds assignment latency. The flow uses the Postgres Outbox for reliable event emission. Dispatch involves a PostGIS query and a Lua scoring engine before publishing via ZeroMQ. Data integrity is maintained with database constraints to prevent duplicate assignments. This architecture enables end-to-end encryption with AI as a virtual signal participant. The server handles key distribution and message relay only, remaining oblivious to content. Client-side encryption and decryption ensure a zero-knowledge server. Observability is E2EE compatible, focusing on structured logs, essential metrics, and distributed tracing without content inspection. Key metrics include request latency, DB pool saturation, and job queue depth. The principle is that you can't debug E2EE content, but you must debug everything else. Backend deployment relies on immutable releases and service discovery via stable DNS. Deployment strategies include rolling and blue-green deploys with connection draining. Hot upgrades are possible, but rolling restarts are simpler and often preferred. Our strategy for scaling Postgres leverages core enhancements first, such as PostGIS for geospatial, partitioning for hot tables, and read replicas. Strategic extensions like specialized search or targeted caching are added only when necessary. The concrete implementation proves that a CRUD, real-time, async, evented, and customizable platform with observability can be built in days using this focused stack. The Boring Strong backend blueprint provides a shippable platform, not just a diagram.